When a ball rolls down a ramp, at some point it reaches its average speed. So the question we want to ask is, where will the ball reach its average speed? Will that occur at midpoint of the ramp? Will it occur above the midpoint? Or will it occur below the midpoint? We're first going to find the time when it reaches the midpoint. I'm going to use this equation here. The average velocity is equal to the initial velocity plus the final velocity divided by 2. And this is one way to calculate the average velocity. The initial velocity is 0, so that gives us average velocity equals Vf divided by 2. So the average velocity will be half the final velocity. I'm going to go ahead and bracket that because we'll come back to that in just a moment. Next, we're going to use one of our kinematic equations. Vf equals Vi plus At. This basically tells you that if you know the initial velocity plus the acceleration times the time, you can calculate the final velocity. Since the initial velocity is 0, we know that the final velocity is equal to At. When the ball rolls all the way to the bottom of the ramp, the time will equal Vf divided by A. I'm going to go ahead and bracket this here as well because we'll come back to that in just a moment. But what if our final velocity is the average speed? Now we're going to compare the time to reach to the bottom to the time it takes to reach the average speed location. So instead of Vf, the final, we're going to use our average velocity here, which is Vf over 2. And don't forget the A, there's still an A here as well. Now notice that if I factor out the 1/2, this is what I get. And by the way, this is my new time, this T prime, I'm going to call it T prime. This is the time to reach the average speed. So T prime is equal to 1 over 2 Vf over A. All I did was factor out the 1 over 2, and we see that T prime, this is the time to reach the average speed, is 1/2 times T, because T is Vf over A, so I substitute T here. So the time to reach the average speed is simply half the time it takes to reach the bottom of the ramp. The next step is to use this time to calculate where is the ball going to be when it reaches the average speed. We'll be using another kinematic equation. This time we're using delta x equals VIT plus 1 over 2 AT squared. Now, VI is 0, so this leaves us with delta x equals 1 over 2 AT squared. I'm going to go ahead and bracket this because we're going to compare this to the location when it reaches the average speed. I'm going to rewrite this equation this time, but this time I'm going to use delta x prime. So delta x prime is when it reaches the average speed. Where's the location? Where's the position when the ball reaches its average speed? So I'm going to do a little substitution. So I have 1 over 2 AT squared, and I know the T is 1 over 2T, so let's go ahead and substitute that in for T. So I'm going to substitute this right here in here for T, so it's going to be 1 over 2T, and this whole value right here is going to be squared. This gives me 1 over 2A, this will be 1 over 4T squared. Now I'm going to factor out the 1 over 4, and that gives me 1 over 4 times 1 over 2 AT squared. Now, have we seen this before, 1 over 2 AT squared? Yeah, we have, right here, right? So we've seen that before. So delta x prime is simply 1 over 4 times delta x, okay? So once again, delta x is the length of the ramp, and so when the ball will reach its average speed is going to be 1/4 times delta x, which means that the ball will reach the average speed at 1/4 the distance of the ramp, which is going to be above the midpoint. If you found this video helpful, check out my next video on inclined planes.